solution, or you can say that the exact solution of the problem, and the approximate solution of the problem, which we obtain by applying the numerical method. Okay, so at each is time step n, we can compute the global truncation error as written over here. We are denoting it with capital En. So that is y at Tn gives you the true solution value, and the y sub n gives the approximate solution value. So this is at any step, time step, we can compute as a global truncation error, while the local truncation error we compute as the difference of the true solution y of Tn and the yn star, which is the approximate solution obtained at the nth step, but assuming that at the previous steps we have the exact solution. So it is specifically giving you the error involved in a particular step. So that is why in case of Euler method, yn star will be taken as y at Tn minus 1 plus h times f at Tn minus 1, y at Tn minus 1. So this way yn star will be computed, and then it will be substituted here, and we can compute the local truncation error. Okay, so this is the about the local truncation error, which is the error involved at a particular step of the numerical method. Okay, so I also mentioned that in computations, actually one another error involved. So computations are usually suffer from round off errors also. Okay, because the computers only have finite precisions, right? So it terminates the digits after decimal, finite number up to the finite number of digits. Okay, so after decimal it truncates. So that is what there will be always a round of error, but in general we know that until your h, the step size, is very small, the global truncation error will dominate. Okay, so with this, now let us move further and try to see that what will be the what will be the order of local truncation error and the global truncation error. Okay, so for that we will start with the test problem. Just a minute. Okay, so let's see. So we will see the local truncation error. For the Euler method first. Okay, so in short I'm writing it as EM. So here we, as you know that, okay, if the test problem is not required, let's take just a general form also, that with that also we can discuss it. So let's take the initial value problem form, which we have considered yesterday. So y dash is equals to f of t, y of t is the equation involved in it, and the initial condition is at y at t naught equal to 5. Okay, over some domain it is considered, and here we assume that the second derivative of y, means y double dash, is going to be second derivative, this second derivative is going to be continuous function. Okay, so basically what we are saying is the true solution of initial value problem will be having the second derivative as a continuous function. Okay, so this you may wonder that if we don't have the solution, then how can we assure about the continuity of this second derivative of the solution? So in this you may note that in this regard you may note that y double dash, actually continuity of y double dash is equivalent to say that the function f sub y and f sub t, these are the continuous functions. Why? Because by chain rule you can write down the second order derivative of y as the d by dt, the first order derivative of y dash, which means nothing but the derivative, total derivative of f function with respect to t. Okay, then by chain rule you understand that it is nothing but f sub t plus f sub y into f. We just apply the chain rule over here and you'll get this. So by noting this, we understand that the continuity of f sub y and f sub t will give us the continuity of the second order derivative of y. So in some way, in this way actually, it will be possible to understand the continuity of the second order derivative of y. Okay, so with this assumption, now if we expand y at tn plus 1 using the Taylor series about a point t equal to tn, what we will be having is y at tn plus h is equals to y at tn plus h times, okay, h is here the difference between tn plus 1 and tn, or you can say that this is this one, or the difference between tn plus h and tn is going to be h. So this is the h term, and then the first order derivative of y computed at tn. Likewise, we can continue. So here, since we are talking about the Euler method, so we are taking the second order term as the remainder term. After that, every term as a remainder term. So we say that the last term here will be this, where xi n belong to the open interval tn, tn plus h, or tn, tn plus 1 also you can write. So using Taylor series expansion, we are expanding y at tn plus 1 about a point ytn, which gives you this expression. So from here, what we get is the following. This uh, we can write this part as h square y double prime. Part is the remainder term here, and then further what we know is the yn plus 1 star. Okay, this we can evaluate using the y value at the previous step as a true value. So with the help of Euler method, this comes out as y at tn plus h f tn y at tn. Okay, so now we have this approximate value, this value of true value of y, okay, at the point tn plus 1, okay, and at the same time we have computed the approximate value of the solution at point n plus 1. Then taking the difference of it, we can write down the local truncation error as per the definition. Okay, so this comes out as local truncation error, the difference which I just mentioned. So this will be nothing but y at tn plus 1 minus y n plus 1. Okay, so we can denote it by t with suffix n plus 1, or as I mentioned earlier, small e with suffix n plus 1. Whatever notation you would like to use, you can use. Okay, so if you do this with the help of this equation number 1 and equation number 2, this right hand side difference can be obtained, and we see that these first two term will get cancelled, okay, because this is nothing but y dash at tn, right, as per the equation. Fine, so first two term will get cancelled and we left with h square by 2 y double dash psi. Okay, so this will be coming out as the truncation error at the step n plus 1. Okay, so from here we can write that mod of en plus 1 is nothing but less than equals to 1 by 2 mh square, if m is giving us the maximum value of y double dash t, where t is belonging to your interval t naught t. This is the domain over which the initial value problem is considered. Okay, so if we take this maximum of y double dash, we can find like this, or in general we can say that the truncation error is bounded by 1 by 2 mh square. Okay, so in this way, so here for n plus 1, the same way you can write for n also. At every step it is this. So what does it mean? It means the local truncation error involved in the Euler method is of order h square. Okay, so local truncation error is of order h square, which means we say that this, we denote it like this, okay, order h square. So this is the thing, okay. So here you may note that this bound m may not be easy to compute or sometimes may not be possible, as I mentioned that it is bound for y double prime. But if you note down this fact that y double dash can be written in terms of f sub y and f sub y, then sometimes it will be possible to obtain an error bound of y double dash even without knowing the true solution y of t. Okay, but the above all these things, the important point here is that this estimation gives us the order of the local truncation error, which is h square. Okay, so this is the implication from this estimation. Okay, so in general what we can say that, so in general for any numerical method what we can say that the local truncation error with order say p, in case of Euler this p is 2, in h, if it satisfies the condition mod of En is less than equals to constant multiple of h to the power p. Okay, which means to say that mod of En is of order h to the power p. Okay, this is the meaning, and which means your truncation error is approaching to zero at least as fast as h to the power is h to the power p is approaching to zero. Okay, so this gives you the uh, order of the local truncation error. Okay, so this way we can see. So from here, one another thing we may note that the higher the order will implies the faster the convergence. Okay, so local truncation error of Euler method converges with second order, which means here the method is converging with order 2. Okay, method is not converging with order 2, that unit, because it is a local truncation error. So and we are concerned with the global accuracy. Okay, so the local truncation order of local truncation error does not give us the order of the method. Okay, here it gives that with this order our local truncation is approaching to 0. Okay, after computing the order of global truncation error, we would be knowing that in general with what order of convergence the method will converge, and that is known as the order of the numerical method. Okay, so now let us look at the order of the global truncation error. So typically what we know is the order of global truncation error is always one time lesser the order of the local truncation error, which means if the local truncation error is of order h to the power p, then global truncation error will be of order h to the power p minus 1. Okay, so this is typically we know. So what I'm saying is the is as follows, that global truncation order of global truncation error is h to the power p minus 1, or maybe I'll write p here. If local truncation error is known as if of order h to the power p plus 1. And in this case, we say that the numerical method is of order h to the power p. Okay, so fine. So this is what we are saying. So intuitive explanation for having the order h to the power p of for the global truncation error in case the local truncation error is of order h to the power p plus 1 is as follows. So what we suppose here, that the error occurred at each step. Say we have a number of steps involved in this numerical method, which we are denoting by EI. Okay, you say that it is EI for all. Okay, so basically what we are saying is this is the local truncation error. Okay, so for all n steps it will accumulate and it will give us the global truncation error. So what we can write then, the global truncation error will be the summation of EI. I is going from 1 to n. Okay, so if our method has local truncation error of order p plus 1, then we know that mod of En will be less than equals to c h to the power p plus 1. We have just observed it. So by using this part we can written as mod of En less than equals to summation mod of Ei, I is running from 1 to n, which means less than equals to summation I goes 1 to n c h to the power p plus 1, and this summation will give you just the value n because this part is independent of n here, and finally we get mod of En as less than equals to nc h to the power p plus 1. And what is this n? These are the number of total steps involved in the numerical method. So we know that we can write it as the t capital T, the final time minus the initial time divided by the step size h. Okay, so using this we can rewrite this right hand side and it gives us this. Okay, so this whole part, okay, not whole part, sorry, this h will first cancel out. Okay, so from here you can see that this h will be removed, will cancel one h over here and it comes out as h to the power p. So we can finally write it as less than equals to mod of t minus t naught c h to the power p, and this is a constant term. We can denote it by with some other constant, say c tilde, and then we get the estimate for global truncation error as mod of En less than equals to c tilde h to the power p. Okay, which shows that the global truncation error is of order h to the power p. Okay, so so this is by intuition we have calculated, but actually technically it is not correct, because here what we are doing is we are just simply saying that the global truncation error is the sum of the all local truncation errors involved in uh, the steps 1 to n. Okay, so but in actual what happens, that error at each step will be compounded with errors at the later steps. Okay, so that's why in this way the simple addition of all truncation errors we cannot consider. So but in rigorous way also we can prove it. So for that I would like to take the test problem. Okay, so here I'm giving you the proof for it, the rigorous proof of it, that the global truncation error will be of order h to the power p. So for that, let us consider one initial value problem as y dash of t is equals to lambda y of t plus g of t. G of t is some given function of t, so as such it is a linear problem, and it is with the initial condition the same which we have considered earlier. Okay, so this initial value problem we are considering. So now apply the Euler method over here. What approximate solution at step point step 10 step n plus 1 will get? That will be yn plus 1 equal to yn plus h times f at tn, y at tn. So in short, let me write it as fn. Okay, it will be easy in the in writing. Okay, so this part is given as this. F is function lambda y plus g, so use it and it gives you lambda yn plus g at tn. Okay, so this will be the part, and now rewriting it we get this expression. Okay, so this is what, after applying the uh, Euler method, we are getting this expression for finding the approximate solution at n plus 1th step. Okay, so now let us use the Taylor expansion for y at t n plus 1, that is the true value. So using Taylor expansion we can write y at t n plus 1 as y at tn as we have done earlier. Okay, so h y dash at tn will be the next value. The next value will be h square plus but divided by 2 y double dash xi n, where xi n is belonging to the interval tn plus 1. Okay, so here with this we are going, and then we know that this part is we have just obtained as the local truncation error, so we can replace it by en plus 1. Okay, y dash at tn we can substitute from the equation. Okay, so what it gives me then, y at tn plus h lambda y at tn plus g at tn. Okay, so this part, and then okay, this I have replaced, so we can simply write it as en plus. Fine, so with all these things we obtained this first expression as 1 plus h lambda multiplied with y at tn plus h t tn plus en plus 1 on right hand side, and then by taking the difference of actual value and the approximate value we can compute the global truncation error at n plus 1th step. So this will come out as y at tn plus 1 minus y n plus 1. So with the help of this equation and this equation, what we obtain is 1 plus lambda h, okay, y at tn minus yn plus en plus 1, which means the local truncation error at n plus 1 at the step is equals to 1 plus lambda h into the local truncation error at nth step plus sorry, this is global truncation error. So global truncation error as n plus 1 at the step in terms of the global truncation error at nth step, plus there will be some truncation error, local truncation error involved at n plus 1 at the step. Okay, so with the help of this, now we can write down the sequence of um, global truncation errors which has which are obtained at the different uh, steps. Okay, so meaning we are putting n equal to 1, 2, 3, etc. and getting the local truncation error at, sorry, global truncation error at different time steps. So at first step, E1 will be 1 plus lambda E naught plus small e 1, right? So this capital E naught, which is the global truncation error at the initial step, will be 0 here. So simply this part will become E1. Okay, then E2 at the next step, the global truncation error will be 1 plus lambda h e1, capital E1, which we just obtained as small e1. So let's substitute it, and next will be E2. So this will be the global truncation error at second step. At third step, global truncation error, again using this kind of this expression, and then substituting capital E2 from this, what we get here is 1 plus lambda h whole square e1 plus 1 plus lambda h small e2 plus e3. So likewise we can keep on substituting different values of n, and finally we can write capital En in terms of small e, okay, at different steps, and as in the term in summation form we can write it as follows: 1 plus lambda h to the power n minus say ej. You can see that it is following the same thing. Okay, so this finally we obtain as a global truncation error. So here we want to find out its estimation, means mod of capital En we want to see. So for that, first note down the few things. That first of all we know that mod of 1 plus lambda h is always less than equals to e to the power h mod lambda. H is positive, so that's why I'm keeping it outside the modulus. Okay, and So, from here, what we get is 1 plus lambda h to the power n minus j will be less than equals to e to the power n minus say h mod lambda, which is further less than equals to e to the power nh mod lambda. So this inequality we first note, then with the help of this we will estimate now the global truncation error. So therefore modulus of En will be less than equals to summation j going 1 to n, the modulus of this part, which is going to be further less than equals to this. So I'm directly using it and writing it here. Okay, and mod of ej we have already computed. This is local truncation error, so this will be ch square in case of Euler method, right? So this is the thing which we are obtaining. Okay, Now it is going to be here, this NH part we can write as the difference of the final time and the initial time, right? Again with the same argument that n is equals to t minus t naught over h. So NH is going to be t minus t naught, this part. So this will become e to the power t minus t naught by not h is vanished. So this is going to be t minus t naught mod h. Okay, and then c h square. So everything is independent of j here, and so if you uh, use this summation, then from this summation we get simply n over here. Okay, now again this nh will become t minus t naught, so this is going to be less than equal to, so this n with one h here from h square will take, that comes out as t minus t naught c e to the power t minus t naught mod lambda, and this in multiplication. So what we have, this is just a constant term. Okay, so and finally we have that the estimation for ENS C tilde H. Okay, which means the global truncation error of the Euler method is of order H. So it is one lesser than the order of local truncation error. So this is the technically correct proof, okay, which we have done for the Euler method here. Okay, so this is about the order of local truncation error and global truncation error. And since in Euler method we are finding that global truncation error is of order h, it shows that the numerical method, which is known as Euler method, is of order 1. Okay, so it is first order, it is converging with order 1. So this similar way you can find out the order for the backward Euler method as well, and you will find that it is also of order 1. This method is also of order 1. Fine. Now, so these two methods which we discussed are of order 1 only, or we can say that these are the first order methods. So let us now look into the some more methods which are having the order 2. Okay, so second order methods now I am going to discuss. Okay, again not all the methods I am discussing, as I mentioned yesterday. I am going to discuss the two methods, trapezoidal method and Huon's method, and both methods you can verify that will be of order 2. Okay, truncation, local truncation error, global truncation error, in the same way you can discuss them also. So let me now define the trapezoidal method and the Huon's method. So first of all, I am taking trapezoidal method. So please recall that how did we derive the Euler method and backward Euler method. What we did there, we approximated the integral involved into the integral equation by setting the function f as constant. Okay, in case of Euler method, we set it as f at Tn, y at Tn. This is for Euler method we did. And for backward Euler method, we set it as a constant f at Tn plus 1, y Tn plus 1, right? So with the help of that, we approximated the involved integral into the integral equation, right? This was the integral involved over here. Now to get the second order accurate methods, in case of trapezoidal rule, we are going to approximate this integral with the help of the trapezoidal rule. Okay, so for that let me first recall that uh, after integrating this equation, given equation of the initial value problem, we obtained the following integral equation: y Tn plus 1 is equals to y at Tn plus integral Tn to Tn plus 1 of f d yt. Okay, so this we have obtained. So our idea is same, as we have used earlier for deriving the two methods, Euler and backward Euler method, that we are going to approximate this integral part. Integral. Okay. So here we are going to approximate it with the help of trapezoidal. Okay. What does it mean? So basically we know from the physical interpretation of the integral is that this integral is giving us the area under this curve, okay, over the interval t and tn plus 1. So if we see it graphically, what is happening, if this is a t axis and this is f or y dash, okay, f of t y t, then for this interval t and tn plus 1, we are actually looking for this area, right, this complete area. Okay, but in approximation, what we will do, we will try to approximate this area with the area of this trapezoidal A, B, C, D. Okay, so these 2 points I am joining, it is making the trapezoidal A, B, C, D. So this integral is approximated by the area of the trapezoidal ABCD, okay, which we can compute. So how we can compute, because we know what is AD, this is nothing but F sub n, okay, meaning F at Tn, Y at Tn, and this part BC also we know it is, this part is Fn, this is F at n plus 1, okay. This is also known, only this is this, and this part is not known, but we can compute this area. Okay, for that let me divide it into this part, or if you directly remember the formula for getting the area of the trapezoid, then you can use that and can find it out. Okay, so basically we are looking for the area of trapezoid as sum of this rectangle plus the sum of plus the area of this triangle. Okay, DEC. So using that, what we obtained here is the following. It will be Tn plus 1 minus Tn, okay, divided by 2 into f at Tn plus f at Tn plus 1. Okay, so f Tn y at Tn plus f at Tn plus 1 y at Tn plus 1. Okay, this is by the formula of the area of calculating the area of the trapezoidal. Okay, or you can divide it in two part and then also you can compute it. You will end up with this. So Tn plus 1 minus Tn is nothing but h, so we can replace it by h. And as I mentioned, in short, I'm going to write these two things as fn and fn plus 1. So finally, what method we are obtaining is y at Tn plus 1 will be equals to y at Tn plus h by 2 into fn plus fn plus 1. Okay, so this is the trapezoidal method. Okay, and again we may note that here this, okay, so now it is actually for actual value I'm writing, so I have to first replace it with the approximate value, then I can call it numerical method. So please pardon me. So after replacing this actual values with the approximate values, now we will write down the numerical method. Okay. So this will be the trapezoidal method, and here we can note that again, because fn plus 1 is nothing but f calculated at tn plus 1 and yn plus 1. So uh, this formula or this method defines yn plus 1 implicitly. So this method is implicit method. Okay, it is of second order and it is implicit method. So this method is second order accurate, that you can check. So I'm not going into the detail of it. The way I have discussed the global order of global truncation error and local truncation error for Euler method, following that you can find out the order here for this method as well. Okay. So this is the trapezoidal method, and if I apply this method on the same example which I took yesterday. What was the example? We see the improvement in the accuracy. Okay, so what the initial value problem yesterday I considered, it was y dash t equal to 1 minus 2t y of t is in between 0 and 3, y at 0 is given as 1. Okay, so applying the trapezoidal rule means this trapezoidal method, what we get here is applying trapezoidal method. Okay, what we get is the following. Okay, apply this method and substituting your function f as 1 minus 2t1, okay, as given function. Finally we get that yn plus 1 we can compute as 1 plus h by 2, 1 minus 2tn divided by 1 minus h by 2, 1 minus 2 tn plus 1, and this is whole multiplied with y. Okay, so in this way we can calculate. So you will substitute everything here and then we'll collect the terms appropriately to get yn plus 1 in this form. Okay, so with this you will get this thing, and then if for the different step size h we compute the approximate solutions and then write down its L infinity error as we did in the examples of Euler method and backward Euler method, we obtain the following. So I'm giving you these values in the tabular way, and I'm again writing the errors involved in Euler method and backward Euler method for comparison purpose. So first, the step size which we are considering is 0.25. For this, the error involved in Euler method, then the backward Euler method, and then this trapezoidal method I'm writing over here. Okay, so I took this step size says as 0.25, then 0.125, 0.625, and then half of it, which is 0.03125, and this list can be keep on going. So in Euler case, we obtain this much error as L infinity error. Here 10967, and then it is 0.05405. Calculating each and everything in a lecture is not possible, so whatever calculation I have, accordingly I am writing. So for backward Euler method, yesterday we saw L infinity error in this with this step size was this, and then next was 10177, 0.51833, and 0.026218, and with the trapezoidal method what we are getting is the following one: 0.0090254, here it is 0.0022883, then 0.000574006. So you can see that how much improvement is here. Okay, so trapezoidal method is giving much better accuracy, very less error is involved here. Okay, so this is much more accurate than Euler method and backward Euler method. And also we can note that here half the step size leads to about a quarter of the error. Okay, and that is what we are expecting with the second order accurate methods. Okay, so that is what we are getting. Okay, so with this now I move to the next method, which is Huon's method. So here the idea is as follows. So in the trapezoidal method, what we observe that yn plus 1 is appearing explicitly in this method, right? So which may not be easy sometimes to solve for yn plus 1 explicitly, especially when your function f is non-linear. So this method gives us the idea to overcome from it by doing the calculation of approximate solution at any step in two stages. Okay, so what this method says is do is that at n plus 1th stage it calculates the approximate solution first with the help of the Euler method, means yn plus 1 star we first calculate like this. Okay, and then this value, star value, we use into the uh, formula for the trapezoidal method to get the final approximate solution at n plus 1 at this step. Means now the approximate solution at n plus 1 at this step, which is yn plus 1, will be as yn plus h by 2 multiplied with f at tn yn plus f at tn plus 1 yn plus 1 star. Okay, so in two stages this approximate solution at particular step is computed in the Yuan's method. Okay, so this method again provides us second order accuracy, of course, because you are using the trapezoidal method finally. Okay, okay, but here the one point is there, though we have the second order accuracy and we overcome from the problem of calculating yn plus 1 in the trapezoidal rule, here the computational cost will be higher. Why? Because we are calculating f twice. Okay, so this will increase the computational cost, but still it is a second order accurate method. Okay, so now this method, if you apply for calculating the solution of this initial value problem, okay, okay, we can list out, if you apply this, then again we can list out the error involved for the different step size like 0 0.25, 0 0.125, etc. Okay, and we observe that the Yuan's method provides this error. So I'm listing it in this particular table itself. Okay, so this is the error involved here for step size 0.25. Then for next step size, it is this. So what we are observing here is that it is not giving the accuracy better than the trapezoidal method. Okay, it is in fact less accurate than trapezoidal method, though it is still second order accurate. Okay, so it depends on our problem that what method is applicable. So it gives us the second order accuracy, but it is at the same time it is less accurate than trapezoidal method. Okay, so this is for your information I'm giving. Okay, so using this method now we solve this and to get this. Okay, so it's the details you can do at your own. Fine. However, you may note that if your function f is depending on t alone, then there will be no difference between trapezoidal method and Yuan's method, right? Because of the presence of y in f, only this complications of implicitly involvement of yn plus 1 is coming. So if f is complete, it is independent of y, then both methods will be same. Okay, so this is about the Yuan's method and the trapezoidal method. Okay, so with this, I complete the discussion over the single step methods. Okay, though there are many more like Runge-Kutta method, etc. So I'm not discussing all those. Maybe in some other lectures they will be covered, or you may study it for any standard textbook of the numerical methods. Okay, so now I would like to move to the multi-step methods, as I mentioned. Okay, so my plan is to cover two multi-step methods. One is Adams-Bashforth and another one is the Adams-Moulton method. Okay, so so what do we mean by multi-step methods and single-step method? So single-step method means here for computing the numerical solution at n plus 1 at step, we make use of the approximate solution of the problem only from the previous step, computed from the previous step, means y sub n, right? So only one value from the previous step we are using to compute the numerical solution at the next step. Fine. But in multi-step method, a very obvious question come into the mind that if we know the numerical solutions at all the previous steps, say y0, y1 up to yn minus 1 or up to yn, then Can we use all these information for calculating the numerical solution at n plus 1 at this step? Means the solution y n plus 1, right? So will it because in such case it may give us the better accuracy. So here the uh, this question can be answered as yes. Okay, so we can use these all information available from the previous step, and that is what the multi-step methods does. So in multi-step methods, for computation of approximate solution at n plus 1 at this step, will make use of the uh, numerical or approximate solution obtained at the previous steps. Okay, so with that we expect the better accuracy here. So such methods we call as the multi-step methods. So to understand these methods, or to construct these two particular methods which I am going to discuss here, let me start with considering the initial value problem. So far I considered. So here again, my initial value problem is in this form with the initial condition. Okay, so let me call it equation number 1. So initial idea is same. We will first integrate it and we'll write the equivalent integral equation. Integration will be over the interval t and tn plus 1, which after integration of the left hand side gives me y at tn plus 1 minus ytn, which I am taking on right hand side. So it comes here, and then right hand side integral of f t yt with respect to t from tn to tn plus 1. Okay, so this equivalent integral equation we have obtained, and now we will try to approximate the integral involved over here on the right hand side. Okay, so here the approximation of this integral will be different. Okay, so what we do here, we take the interpolating polynomial of degree say k minus 1 to the function f. Okay, and then do the integration of this integral. Okay, so what we are doing is we are taking the, or you can say that we are, okay, so as interpolating polynomial of k minus 1 degree we are taking for the f function. So f t y t we are approximating by an interpolating polynomial of order say k minus 1. Okay, so this interpolation polynomial we can form by using uh, different ideas. Okay, so this interpolation polynomial we can use for the derivation purpose here, and any form of this we can consider. So for most convenient way, adopting the most convenient way, I am going to use here, in fact it is used in general here, the Newton backward difference formula for this k minus 1th degree interpolation polynomial. So using this formula, what we obtain is, first of all we need the interpolating points here. So for forming this polynomial using Newton backward difference formula, we take the time value pairs as follows. Okay, so interpolation and extrapolation, I hope you have already studied in the previous lectures in this FDP program. So if you recall from there are different ways of for generating this interpolation polynomial. So I am adopting one of them, which is known as Newton backward difference formula. Okay, so here, as I said, we form this polynomial of degree pk minus 1 by using time value pairs ti f ti y ti. Okay, for I as n minus 1, n minus 2, and so on, n minus k minus 1. Okay, so or you can say n minus k plus 1. So total how many points we are taking? K many points. So these are k many points, with the help of which we are finding out the k minus 1 degree interpolation polynomial using the Newton's backward difference formula. Okay, so with this what we get is the following. So here integral from Tn to Tn plus 1 f dy of t dt will be then approximated with 0 to 1 summation m, say m going 0 to k minus 1 minus 1 to the power m. This is, sorry, minus s, so this is minus scm binomial coefficient. Okay, then nabla m, mth degree, okay, mth order, sorry, f at tn, y at tn into HDS. This we are getting by setting T as Tn plus SH. So basically what is our k minus 1th degree polynomial here? The polynomial is this one, whatever is written as the integrand over here. Okay, and since we are changing this uh, variable t by setting t as Tn plus SH, the integral limits Tn to Tn plus 1 will convert as 0 to 1. Okay, so accordingly dt will convert to HDS. So these are simple computations. So with this our integral value will be approximated by the expression which I have written on the right hand side. Okay, so this box part is nothing but pk minus 1. Okay, so this is an approximation, so obviously there is some error involved over here. So what I can say that in actual ft yt will be nothing but pk minus 1, the interpolation polynomial, plus the error term, it is kth order derivative of f at xi n y xi n. Okay, this is important from the point of view of calculating truncation errors. So that will be this part. Okay, this will provide us later, so we will see how it helps t minus tn plus 1 minus t. So this is the error term involved over here, but since we are approximating, so I'm just by the interpolation polynomial, so our integral is approximated by this equation. Okay, so in this equation of course we have to then calculate this integral, which we can do, for which we need to calculate the integral of 0 to 1 minus 1 to the power m and the binomial coefficient. Okay, rest of the things are independent of s, so we can keep it as it is. We will handle it later on, and you can see that this integral is possible to evaluate for some different values of m. So for example, if you take m equal to 2, it can be evaluated. Okay, so for m equal to 2, if we calculate it, what happens? It comes out at minus 1 whole square minus s2, the coefficient. So basically, if you just open this binomial coefficient, we end up with the integrand s square plus s ds. Then evaluating this integral after substituting the integration limit, it comes out as 5 by 12. So likewise, for different values of m, we can generated. Okay, so and you know that m is depending on k, which is giving us actually the k minus 1 is the order of the interpolation polynomial. Okay, so depending on the degree of the interpolation polynomial, you will get the value of m, and accordingly the terms will appear into this approximation in summation part, and this involved integral will be calculated. So for different value of m, we get the different value of this integral, which we can list it out, and accordingly we can write the approximate value of this integral. So that is what I'm going to give you next. So if m value is 0, then 1, then 2, then 3, then 4, etc., this integral, if I denote the I, this integral will be having value 1 in case m is 0. M is 0 means what? There is nothing, so you can easily check it. M is 0, this will be simply coming out as 1. Okay, so it will be very simple computation. If m is 1, then m is 0 means this initial stage, okay, only one term in this summation. So accordingly we can compute 1. If m value is 1, we will obtain 1 by 2. M equal to 2, you have just calculated, it is 5 by 12. Then for 3 it is this, and likewise we can compute. So this kind of thing is happening, and therefore from this equation, say this equation number 2, we get the approximate integral value, and we can say that not 0 to 1, it is, so therefore we understand that integral Tn to Tn plus 1 of ft by t dt will be approximated with h f Tn y Tn, that is the first term over here, okay. Okay, then the second one is h into 1 by 2. Here this will be corresponding to the second term, so h by 2. Then lambda f at Tn by Tn. Then the third one, 5 by 12h, you will get lambda square f Tn y at Tn, etc. Okay, so this way it will keep on. It depends now the order degree of the polynomial, that how many terms will appear. So just look at this. This summation part will come out with this h into summation of m equal this h into lambda y f t and y t n will be outside, and this integral of this you will be having for corresponding to each value of m in this summation. Okay, so accordingly these many terms will come. Okay, so that is what is happening. So we can simply write the numerical method as yn plus 1 after approximating the exact values with the approximate values, that it will be yn plus h times the integral, okay, this uh, yn plus this tn plus t, this integral value, so it gives us h into f tn yn plus half gradient lambda of f tn yn plus 5 by 12, h is taken out common as a common one, so lambda square f dn yn, etc. Okay, so this will be the numerical method which we will obtain depending on the degree of the interpolation polynomial. Okay, so for k equal to 2, if you write it, so in the case of k equal to 2 means interpolation polynomial is of degree 1. Okay, so in this case what f is approximated by interpolation polynomial of degree 1, and therefore from this equation we obtain the numerical method as yn plus 1 is equals to yn plus h f e n yn plus half lambda f t n yn, and we know that what is the meaning of this lambda. We can use it, we are using the Newton backward formulas, backward difference formula. So it will open as fn minus fn minus 1. Again, short form I'm using. Okay, so this gives you yn plus 3 by 2h. After simplifying the things, this is also fn. So you get 3 by 2 f h fn minus h by 2 f n minus 1. Okay, so this will be the numerical method which we obtain in case the function f is approximated by the interpolation polynomial of degree 1. Okay, and this is known as second order Adam-Bashford method. Okay, and the small n here will run from 1 to up to the number, say, n minus 1. Okay, so basically to get here the values, you can start from y2 calculation of the approximate solution. We can start from the second step. Okay, here the first step and the 0th step, it must be known to us. Okay, then we can calculate it. So that is the limitation with this. So what happens when we apply such methods? We calculate the approximate solution at the previous step with the help of any single step numerical methods, okay, like your of the similar accuracy. Okay, so so that we get the good solution. Okay, so by using the single step methods, we obtain the numerical solutions or the approximate solution at the previous steps, and then using them as the initial values over here, we start calculating the approximate solution in the later uh, steps with the help of Adams-Bashforth method. So this is the second order Adams-Bashforth method. In the same way, you can calculate the third order, fourth order Adams-Bashforth method. And this order means it gives us the accuracy also, that this method is of third order accurate or second order accurate. So the same terminologies we use for single step method suggests that here the method will be of second order accurate. Okay, so for k equal to 3, if you go for then third order accurate method, you will get again Adam-Washburn method, but f will be interpolated by the second degree polynomial. Okay, and in that case, if you follow the similar steps, you will get the numerical method as follows. Okay, so likewise, you can calculate or you can write the formulas for different order Adams-Bashforth methods. So fn minus 1 plus 5 by 12 at fn minus 2. So this will be third order Adam-Bashforth method. Okay. So likewise we can do, and accordingly accuracy will be improved. You may note that if we interpolate, if we take k equal to 1, meaning we are just interpolating f with with the polynomial of degree 0, which means the constant, then this method will converge to the Euler method, which is quite obvious, right? So as I mentioned, so in multi-step method, the important point to note is that we need to calculate the first uh, the first few steps, we need to calculate the approximate solution with the help of the single step numerical methods. Okay, and these methods should be of comparable accuracy to start with. Okay, so this is the about the method. Now if we talk about the local truncation error involved in it, that the idea will remain same as I discussed for the single step methods. So if I go back here into the approximation part for the function f, I mentioned that this is the error term involved in the approximation. Okay, because f is approximated to k minus 1. In actual, it is having some additional term. So this additional term, we can say that is the error term involved in when we approximate f by pk minus 1. Okay, so with the help of this error term, we can understand the local truncation error. Okay, so what it would be? Okay, sorry, I think there is some, this is stuck. Just give me 1 minute. It seems that it is stuck somewhere. I'm sorry for this inconvenience. Actually, my OneNote is stuck. Please give me 1 minute. I'll just restart it. Dr. Rahul, just give me 5 minutes. I'll just resolve this issue. This window is not closing. Again join. Leaving the. I'm leaving and then I'll rejoin. I hope it's okay. Hello. Okay, I think it's working now. So I'll go back to my notebook. Okay, can someone please confirm if my screen is visible and I am audible? Okay, thank you. Okay, so Adam-Bashford method we have derived. Now, let us start with the local truncation error for it. So, as I mentioned, so we will make use of this error term involved in the approximation of the function f. Okay, this error term. Okay, so if here in this we set again we do this setting as t equal to tn plus sh. So in so this is the error term over here in the approximation of in f. So in turn when we substitute the exact value here in this integration, so this term will come with the integral value 0 to 1 with the setting as t equal to tn plus sh, and the integral will be with respect to s, like we have done for the approximating the integral, okay, that evaluation. So using that, what we get is the following. We have to evaluate this integral. 0 to 1, the kth derivative of f xi n y at xi n divided by, if this is small, I have used k, so factorial k, then sh, the other terms will change like this. Okay, so sh, t minus tn comes out as sh, then tn plus sh minus tn minus 1, and the last term will become tn plus sh minus tn plus 1 minus k. So basically t is replaced by tn plus sh. So with the help of that, we obtain these terms here, and then h ds. Okay, so t is replaced by tn plus sh. So with this error term will be there in the evaluation of the integral term. Okay, so here we first note that this will become simply h plus sh. Why? Because tn minus 1 is nothing but the step size h. Similarly here, and in between terms also we can write accordingly. It will become k minus 1 into h plus sh. Okay, so with this, now we have 0 to 1 sh into s plus 1 into h, sorry, and then the last term will be here s plus k minus 1 into h. Okay, these are these terms written over here. These terms I am writing simply. Okay, and then the k derivative of f at xi n y xi n divided by factorial k, and this h's. Okay, so simply this we are doing, and then you can understand that this uh, h uh, from these from this product, h to the power k will come. Okay, in a because h is present k times in a product, so h power k will come, and one h is sitting over here, so it will become h power k plus 1, which I can take outside the integral, because integral is with respect to s, and also we know that this term is independent of s, so that also I can take outside the integral. Okay, so if we do this, then the integral will be for 0 to 1 with the integrand s plus 1 and so on, s plus k minus 1 ds. Okay, that integral we can do, and for that, now what I do is I use one trick. Minus 1, I take minus 1 to the power k in multiplication, and the same minus 1 to the power, actually the plus 1 I am writing as minus 1 to the power 2k. So 1 minus 1 to the power k I'll keep as it is, and another minus 1 to the power k in present in a product I am distributing over here. Okay, over this product in the integrand. So this will be minus s then, and it will be then minus s minus 1, this is minus s minus k minus 1. Okay, so likewise it comes. Why I'm doing this? Because with the help of that I can see this integral as integral 0 to 1 of the coefficient fact, binomial coefficient. Okay, minus s ck. Okay, this I can see minus 1 to the power k, and this we have evaluated earlier for different values of m there. Here we can do same for different values of k. So this evaluation already we have done, we can make use of it. So what we obtain is actually the following. Okay. So with this we understand that this integral is can be evaluated, and finally the local truncation error involved in it comes out in this form, and which shows that the local truncation error will be of order k plus 1. Okay, in case the method, in case you take uh, the approximation of the function f with the interpolation polynomial of degree k minus 1. Okay, so it means if we take the example of third order Adams-Bashmore method, what we observe is this will be the case of k equal to 3, and then immediately the truncation error here will be h to the power 4, fourth order derivative here, okay, with whatever these things are, divided by factorial. Okay, this factorial is going to be vanished actually. I forgot. I'm sorry, because this factorial we have to take inside, then only this will become the coefficient. Okay, then only it will become the coefficient, binomial coefficient. So this will not be there. It will not. It should not appear, and actually it will not be. Okay, so that is merged into it. So there is nothing here in the denominator. This will be simply this, and then we have this integral, which can be evaluated, right? So here it is 4, so this will become k is already 3. So basically I can put that also. So it will give me minus value, and this will be 3. This is 3 and this will be minus 1. Okay, so and then if we calculate this integral, or you use the list which we have made for different values of uh, m there, and in our case now the k is 3, so it will come out as 3 by 8. Okay, so this can simply replace by 3 by 8, and we end up with 3 by 8 h to the power 4, and this is a fourth order derivative of f, meaning, sorry, it is third order, k is 3, so it is a third order derivative of f. It means it can be replaced by fourth order derivative of y at psi, okay, by the equation. So this will be the truncation error. It shows that en plus 1 is of order h to the power 4. Okay, so here local truncation error is of order h to the power 4, and global truncation error will be of will be of order h bar 3, and therefore our method is known as the third order Adam-Bashford method. Likewise, you can check the truncation errors, local truncation error as well as global truncation error for other methods. Okay, so idea will be same as the single step method. Only thing is you have to calculate it the way you have you are approximating the integral value here. Okay, so with the help of that we end up with the this much local truncation error here. Okay, so this is the discussion about Adams-Bashford method, and this method is explicit method. You may observe that yn plus 1 is appearing explicitly here, so this is explicit method. Now next method is the Adams-Moulton method. Okay, so Adams-Moulton method is implicit method. Okay, here there will be a slight change in the approximation of the integral. What we do, we approximate here the function f by the interpolating polynomial of degree k minus 1, as before we have done in the earlier method, but here interpolation points will be slightly different. Okay, so based on that the method will get change, and we end up with the implicit method which is known as Adams-Moulton method. Okay, so I'm going to make use of the steps which I have written, which I have already written for Adams Bashford method. Okay, I will let you know where the changes are coming, and accordingly we will write down the Adams-Moulton method. Okay, so this is going to be Adams-Moulton method. Now, so as I said, let us go back. In this Adam-Bashford method, uh, like Adam-Bashford method, f function will be approximated by the interpolation polynomial pk minus 1 of order k minus 1, But now the time value pairs will be for ti f ti y ti for I equal to n plus 1 and n minus 1 etc. up to n minus k plus 2. Okay, so here this interpolation point is added, tn plus 1 f tn plus 1 y tn plus 1. This point is added, but in total again these interpolating points are k numbers. Okay, so k many points again we are using. So this is the change over here, and because of that there will be change, in the change, there will be change in the formation, in the formula for, or you can say this the expression for the polynomial pk minus 1. Okay, so because of that there will be small changes in the integral value which we will compute, approximate integral value, and that will give you the final uh, numerical method, implicit numerical method known as Adams-Moulton method. Okay, so let me tell you what is the polynomial here. Now this interpolation polynomial which we will construct again with the help of the Newton backward difference formula will be as follows. So summation will go from m0 to k minus 1 minus 1 to the power m, and now the binomial coefficient minus, sorry, 1 minus s c m. Okay, so this will be 1 minus s c m lambda m f t n plus 1 y at t n plus 1. Okay, so this will be now the interpolation polynomial. Fine, so using this now we will calculate the integral as we have done for deriving the Adams-Bashford method, and what we obtain is the following: yn plus 1 yn plus summation m going 0 to k minus 1 lambda m f at tn plus 1 y at tn plus 1. Okay, h minus 1 to the power m, integral will be from 0 to 1 m, the binomial coefficient here ds. Okay, this is again with the same setting which we have done earlier. Okay, t is taken as tn plus sh. Okay, so all these same steps, only because interpolation points are changed slightly, so though they are same in total numbers. Okay, if the interpolation polynomial will get slightly changed, and therefore after evaluating the approximating integrals, that is this part. Okay, this integral. Okay, we get the different form of the numerical method which is implicit in y n plus 1. Okay, so here you can see that binomial coefficient is this. There in the this method, Moulton method, we have this, so obviously there will be difference, and also f is taken at tn plus 1. Okay, f by tn plus 1. So that's why there will be a change, and finally we end up with this kind of form. Now depending on the value of this integral, we can write down the numerical method. So here after calculating this integral, we observe that in general this Adams Moulton method's formula will be as follows: h f n plus 1 minus 1 by 2 lambda f n plus 1 minus 1 by 2 12 lambda square f n plus 1 minus 1 by 24 lambda cube f n plus 1, and so on. Okay, so depending on the degree of the interpolating polynomial, the total number of terms will appear in this expression sitting inside the big bracket. Okay, so this is the Adams Moulton method. Okay, so here you may note that if we take the values n as 1, 2, 3, etc. up to n minus 1, so to it also starts from, okay, it depends that from where it is going to be happen. So in different cases it will be different, so let me not write it in general. Fine, so this is Adams Moulton method, as I said. So putting the different values of k or different cases of k, we can find out the different order uh, Adams Moulton method. So for example, if you take k equal to 1, we can observe that for the case of k equal to 1 means if you take the interpolation polynomial of degree 1, then Adams Moulton method will convert to the backward Euler method. Okay, so you can easily observe that, because then it will be yn plus 1 equal to yn plus h fn plus 1. Okay, so that will convert into the uh, backward Euler method. If we go for the second order, up to second order means we take the case k equal to 2, then it will convert to the trapezoidal rule, because up to here the terms will come and it gives you the trapezoidal method. So you can easily verify it. And for k equal to 3, so in this case it will be second order method, in this case it will be first order method, and if k equal to 3, then we get the third order Adams Moulton method. Okay, and then we will be having these many here. If it is a third order, then up to 1 by 24, this kind of thing you'll get. And the formula comes out as yn plus 1 is equals to yn plus h by 12, okay, 5 fn plus 1 plus 8 fn minus fn minus 1. Okay, so you can see that you, to get the numerical solution at n plus 1 at this step, we need the approximate solution at the step n and n minus 1. So the two previous step we need to know the term. So here n will start from 1, 2, etc. up to n minus 1. So, and as I mentioned earlier, for Adams-Weismann method, here also the approximate solution at the previous step will be calculated with the help of the appropriate single step method. Okay, meaning the single step method with the acceptable accuracy. Fine. So with that, we will be able to calculate the uh, approximate solution at the different steps. Okay, so here accuracy will be of different order, like the Adams-Bashforth method. Okay, so same way you can follow this procedure for getting the local truncation errors, etc., and can say that in this case k equal to 3, your local truncation error of the method will be of order h power 4, while the global truncation error will be of order h cube, and thus our method will be known as the third order accurate method. Okay, so if you wish to note here local truncation error, which we can calculate like the previous method, it comes out as minus 1 by 24 h power 4, and then the fourth order form y. Okay, so this will be the local truncation error involved in the third order Adams Adams Moulton method. Okay, so this is the idea about the Adams Moulton method and the error involved in it. So if we apply those methods on the initial value problem, then we can see that how accurate they are. Okay, they are multi-step method. We can check their errors and involved. We can see that how much errors involved into it. Okay, so for both the method, applying for both methods, I'm taking the same problem. Okay, so this is my equation over here. It's different from the earlier equation. You can apply the single step methods also, can compare the solutions and the error involved in this. You can see which one is better. Okay, so here find the approximate values or approximation of the solution. Find the approximate solutions using Adams-Bashforth, say fourth order, and similarly also we are going to use Adam Moulton fourth order. Same order method, let us apply and see that how much error we obtain. Okay, for this, let us take the step size as 0.2. Okay, so total number of points here will be 0, 1, 2, 3, 9 and 10. Okay, so 10 intervals over here we will be having. So fourth order Adam-Bashforth method, if you apply, then what happens? So fourth order Adam-Bashforth, let us apply. So according to the method formula, we will be having yn plus 1 is equals to yn plus h by 24, 55. F is to be calculated at tn yn, okay, minus 59. F is to be calculated at t minus 1, yn minus 1, then 37f, tn minus 2, yn minus 2. This is I am writing as per the fourth order Adam-Bashforth formula. Nothing nothing is special in it, very simple, just the substitutions. Okay, and this we can write for n 3, 4, 5 up to n. Okay, so what we need to calculate the approximate solution at the previous step, because here from y4 onwards we can calculate. So what we need: y0, y1, y2 and y3. Okay, so y0 obviously it is given to us here is 0.5. y1, y2, y3, these approximate solutions means the approximate solution at first, second and third step we will evaluate with the help of any of the single step method. Okay, so here for example you can use fourth order Runge-Kutta method. Okay, it is a fourth order method, so it will be it will give us the good accurate good compatibility, right? And also because this problem is simple, exact solution is obtained, so here in fact direct exact solutions also I can use. Okay, so but in actual we don't know the exact solutions, so of course we need the numerical method, any single step numerical method, okay, like Runge-Kutta method. So with the help of that, these three will be calculated. What else we need to substitute in this formula is h, which we know as 0.2. Tn's we know here. Okay, so t naught is 0, t1 will be your 0.2, t2 will be 0.4, t3 will be 0.6, etc. Right? So accordingly you can put the values over here, andyn's meaning y0, y1, y2, y3 we have already, we will calculate. Then with the help of that f will be calculated. And what is f here? F is given as, so ftn, yn is nothing but yn minus tn square plus 1. So using this, these f will be calculated at the different steps, tn, tn minus 1 and tn minus 2. So once you do this, we'll substitute everything into the formula and we start computing the approximate solution at the fourth step, fifth step, etc. Okay, so you can do like this and can list all these approximate solution in a table and calculate the error by taking its difference with the exact solution at these step, at these time steps. Okay, so if we are doing this, so exact solution you can note here. So exact solution will be, sorry, so exact solution y of t for this problem is t plus 1 whole square minus 0.5 e to the power t. This is the exact solution to calculate the exact values at the different step points, time steps. Okay, and then approximate we will calculate, and if I make a table for it, it comes out like this. So pn's, then exact value, then the values which we are obtaining with the help of Adam-Bashforth method, and then error we can calculate by taking the difference, and the same problem we'll evaluate with the help of Adam-Moulton method, following the similar steps as which I mentioned for Adam-Bashforth, and we'll calculate error. Okay, so here initially the values will be calculated up to zero point 0.4. Okay, here in fact for Adam dashboard up to zero point 0.6 we'll calculate and start from the zero point 0.8. Okay, so this is going to be calculated over here. So I'm not listing everything, just first few values let me write down, and it will keep on going up to 2. Okay, exact value in this case 1.6489406 kind of. Here we'll calculate, we will be having it as which we obtained from the earlier method. Okay, so that's why I'm not listing here. For zero point 0.8 it is coming 2.12722295. For Adam dashboard method, when we apply it, the value comes out like this. Then error involved is this. So it is fourth order. Okay, clearly it is fourth order. For Adam Walton, even for zero point 0.6 we can calculate, because in this case we need only to calculate in a prior at T0, T1, T2. Okay, so this T3, at T3 we can calculate it. So that is giving us this value, and error involved is this much small. Okay, and for the next step is zero point 0.8, Adam Walton will give this value. Okay, so again it is very small. Okay, so you can see clearly see that fourth order approximation we are getting. So implicit Adams model Moulton method gives even better results than the explicit Adams Bashford method of the same method. Okay, so in fact in general it is true, but the limitation here with Adam Moulton method is that yn plus 1 appears implicitly. Okay, and it will not be always easy to finally write your numerical method for calculating yn plus 1 in the explicit form of yn plus 1. Okay, so in such cases what we do, we, as I mentioned earlier also, we need to use some iteration method, okay, like Newton-Raphson method or the secant method. Okay, so in some stages when f is non-linear, this situation will arise, and then whatever expression for you will get for your numerical scheme. For example, suppose you have something like y2 is equals to some constant multiple of y2 square plus another constant. Then in such cases, suppose this is the situation, I'm giving you just an example because we don't have much time to give the details of it. So here, this kind of situation, suppose we end up after applying the Adams-Moulton method, then we to evaluate this y2, what we can do, we can use the Newton-Raphson method. Okay, with the help of that, this non-linear equation for y2 you can handle, and iteratively you can calculate y2 and then see the final uh, approximation or the approximate solution at this step. So likewise you can move on. So I am assuming that you are well aware about these iteration methods. Okay, and so that's why I'm not giving the detail over here for how to apply this method further. Okay, so in such situation only the idea is to go for the iteration methods. So that is about this. Okay, so this is the two methods which I wanted to discuss under the multi-step methods, numerical methods. With this, now I move to the predictor corrector methods. Okay, so I'll give the idea of it, and then I will move to the stability discussion over the stability. Okay, so what I can say here is this, just now I discussed that we could use the Newton-Raphson method or the secant method we can use to approximate yn plus 1, means the approximate solution at n plus 1th step. However, this may also be complicated. So this procedure can also be complicated, right? Or you can say that computation cost will also be high in these cases. So then what is the use of this kind of implicit methods, etc., right? This is the obvious question. So what in actual happens that implicit methods we generally don't use as we have discussed, means as we have discussed, to apply it directly for solving the problems. Instead, what we do, we use them to improve the approximations which we obtain by using the explicit methods. Okay, so in this way, what in actual we are doing, we are uh, trying to use the combination of explicit and implicit method, and this combination of explicit and implicit method is actually known as the predictor corrector method. So in simple words, I can say that in predictor corrector method, the explicit method is used as a predictor method, while the implicit method is used as the corrector method, because implicit method will correct or the um, value of the approximate solution at some step, say n plus 1, which we use with the help of the predictor method, okay, which is actually an explicit method. Okay, so to improve the accuracy. Okay, so that is the idea. So we can simply state predictor corrector method as a combination of explicit and implicit method. And here the implicit methods play a very important role. In fact, these implicit method we use iteratively also until the convergence is obtained. Okay, so to understand it, let me illustrate this predictor corrector method for the test equation. So what is the test equation? Y dash t equal to lambda y. Okay. So here, for example, I'm taking the predictor method as the Euler method. So in this case, n plus 1th step, the approximate solution will be yn plus h f at t and y. Okay. So this is going to be Euler method. Okay. And as a corrector, I'm using trapezoid. Okay, so this gives us now the approximate solution at n plus 1 as yn plus h by 2 f h t n plus 1 yn plus 1 plus f t n y. Okay, so what is happening here? This yn plus 1 in the computation of this function f will be the one which we will obtain with the help of the predictor method. Okay, is using the Euler method. So here this Euler method is playing the role of predictor, while trapezoidal method is playing the role of corrector. Okay, so this combination of explicit and implicit method gives us the predictor corrector method. Sorry. So more precisely, I can say that as a zeroth iteration, yn plus 1 we are obtaining as yn plus h f en yn, and then the next iterations, okay, it is jth iteration, we can take, we'll use the zeroth iteration of yn plus 1 to calculate it. So yn, and it comes out as yn plus h by 2 of f t n plus 1 yn plus 1, the j minus 1th iteration of it, okay, plus f t n y. Okay, so this j will be 1 2 and so on, say m. So if m times iteration you do for the implicit method. Okay, so in practice what we observe that generally the one time or the two time application of the corrector is sufficient to get the improvement in the accuracy. After that, not much accuracy is seen to be improved. Okay, so that's so it is not going very expensive here. Just one or two time iteration at the corrector step, we get the good accuracy. So that is the idea about it. Okay, so this is about the predictor corrector method. Now the thing is, what is the guarantee that this method will converge. Okay, so basically for this case, uh, for this point of view, we know that it is going to be, okay, so this will converge because we can here also can discuss the local truncation array, etc. So basic idea will remain same obviously. So what we do, we just what is the plan now, that we'll compute this local truncation error, and we'll see that what order of local truncation error will be obtained over here. Okay, so what we see is, so if there is with the help of the order of local truncation error and global truncation error, again we can talk about the that method is converging with that much order to the solution. Okay, so here for this zeroth order, what we have is the following for this test problem. So this test problem, according to test problem, f function is lambda y, so that's why it is coming as lambda yn, and therefore I'm getting this solution as follows. I'm not going to write it over here. Let me write it separately. This is going to be 1 plus lambda h yn. Okay, then the next step is the corrector step, where first iteration will give you something after using the trapezoidal method. So it is lambda yn plus 1, 0th iteration, plus lambda yn. Following this, we get it as yn 1 plus lambda h plus 1 by 2 lambda h square. Okay, so this way we can keep on continuing, and we say that at mth iteration, what we obtain is this yn multiplied with 1 plus lambda h plus 1 by 2 lambda h whole square, and so on. Or this term will be lambda h cube by 2 square, plus so on. The last term will be lambda h to the power m plus 1 divided by 2 to the power m. Okay, so we can see the appearance of the geometric series over here, because we can rewrite this part as 1 plus lambda h into 1 plus p plus p square, and so on, p to the power m. Okay, where p is taken as lambda h by 2. So this is becoming a geometric series which can be summed up as 1 minus p to the power m plus 1 divided by 1 minus p, of course when p is different from 1. So this is a finite number of terms showing over here. So 1 minus p. Okay, so this is the case which we are obtaining, and then we can say that yn plus 1 at mth iteration comes out as yn into 1 plus, okay, let me write it little up. This is 1 plus p minus 2p to the power m plus 2 divided by 1 minus p. Okay, this is just the sum in between p within a bracket I am rewriting. Okay, so this let me call as a star the equation. So this is going to be sum up. So what happens now, if f tending to infinity means number of iterations we are increasing, then this equation, this will converge, right? This will yn plus 1 will definitely converge. You can take y m tending to infinity, and when it will converge, when your ratio of the geometric series will be less than 1, which means lambda h by 2 modulus will be less than 1, which means you can say that mod of lambda h is going to be less than 2. Okay, so from here either you understand it, or from here itself you understand. See, if m is tending to infinity, we'll end up with the geometric series, infinite geometric series, and the sum of it will be 1 over 1 minus p, provided mod of p is less than 1. Okay, so in this case the series will converge, and you can write down this sum. So that's why we are saying that this as m tends to infinity, this equation will converge if mod of lambda h is less than 2. Okay, so with this condition, the convergence is achieved. Okay, but at the same time we know that what is the exact solution. Okay, this is the approximate solution as n plus 1 we have obtained. So now, use writing the exact solution for this test problem, we can compute the local truncation error also. Okay, so y at t n plus 1 for this simple problem will be e to the power lambda h y at tn, right? It is simply the, it's a very simple form, separable form. So by integration on both sides, you can calculate it. So this is the exact solution over here, and therefore the local truncation error involved in it will be the difference of the exact solution and the approximate solution. Okay, and that comes out as e to the power lambda h. Okay, this is y at tn minus, you can substitute this value after taking p in this as lambda h by 2. So it comes as 1 plus lambda h by 2 minus 2 lambda h by 2 to the power n plus 2 divided by 1 minus lambda h by 2. So this part. Okay, and this whole with y at tn. So this will be the local truncation error involved in it. And from this, you can understand that what happens if corrector is not at all applied, and if it is applied one time, and if it is applied two times, etc. So here you can do for this. So if we don't apply the corrector, means m is 0, right? So if you substitute m equals to 0 here, then by simple calculation of this formula, we see that the error appearing in this will be 1 by 2 lambda h square plus another terms, if we say, that will be of order lambda h bar cube. Okay, a mod I should put here, mod. Okay, so this is the case when we zero time correctors are taken. Okay, so simply explicit method is applied. But suppose we apply the corrector one time, then what happened? We get the error as 1 by 6 lambda h cube and then order of lambda h 4. Okay, other terms are of order h power 4 onwards. Okay, so this is the time when we apply the corrector one time. So implicit and explicit method both are there. So first explicit method and then the same will be improved with the help of one-time application of the implicit method here. But suppose we do the iteration here for the corrector uh, method. So two times corrector method is applied. Then what we see that error appears as minus 1 by 12 lambda h cube plus order of lambda h cube. Okay. So this is the case. And after that we see no improvement. One more time, if the corrector method is applied to improve the accuracy, we see no correction or no improvement. Okay. So what it shows that application of the corrector more than twice is not improving the result. Okay. So hence in practice, generally the one or two time application of the iterative application of the corrector method gives us the nice results. Okay, so this is this calculation I have done for the test problem, and which itself is showing this part. Okay, so this is the way we can understand that how the predictor corrector method are used. Predictor corrector methods are used to compute the solution, approximate solution of the initial value problem. So in this sequence, in place of this Euler method as predictor method, trapezoidal method as a corrector method, any explicit method can be used as predictor method, and any implicit method can be used as the corrector method. For example, if we want to make use of the multi-step methods, so what we can do, we can make use of the Adams-Bashforth method of any order. Suppose third order we are using, then it can be third order Adams-Bashforth method can be used as predictor method. Then the third order Adams-Moulton method we can use as the corrector method. Other things will remain same. Okay, the application of these predictor corrector method will work will be will be there present in the same way, or we can be carried out in the same way. Okay. So this is the thing. So the same initial value problem which we have solved just now with the help of the Adam Bashford method alone and Adam Moulton method alone. Now we can solve with the help of the predictor corrector method. Okay, so here we can compare these results. So and you will find that it will give you the even better result if you apply the predictor corrector method. So that you can see. So here it is done for Adam Bashford, Adam Moulton method, but the same we can do with the help of predictor corrector method, in which Adam Bashford method is used as a predictor method and Adam Moulton we will use as the corrector method. Again, for both we will use as the fourth order accurate method. Then comparison will be good enough to judge upon the accuracy of the solution. Okay, so apply the fourth order Adam Washburn method as predictor and fourth order Adam Moulton for fourth order for as a corrector method, and then you just list out the error involved in this method, and by comparison you will understand that which method is more accurate. Obviously you will get find out as a result that predictor corrector method is giving the best result among these. Okay, so that I'm not doing. So the same example you can try with this for this. Okay, you can write the program also for making this table. Okay, so this is about these multi-step methods and predictor corrector methods. uh, so I'm also asked to discuss the stability part. So I don't think that I have much time for doing this. So just another 5 minutes. I'll brief you about this, a general idea of the stability of the numerical methods I'll give you. Okay. So for this, I'd like to go to the next page. Okay. So here I have prepared it for you. So what we can understand by the stability of the numerical method. This is the first part of it. Okay, so what do we mean by stability? So a numerical method, as I've written here, is said to be stable, or we call it as a stable numerical method if the total accumulated error, which also include the round of error, is bounded. Okay, so it means the error, total error, which is involved in this uh, involved in the computation of the approximate solution using the numerical method. If we see if we calculate and find that it is bounded, then numerical method will be stable. Okay, so that is the idea. So again, to understand it in a better way, let me uh, let me consider the test equation y dash equal to lambda y. Lambda can be real, it can be complex as well. Okay, initial condition is y t naught equals to 0. So exact solution will be this y naught e to the power lambda t minus t naught. If I make use of the initial condition, I can easily write it. Okay, so from this, what we can do further, we can write down the y at tn plus 1 in terms of y tn by uh, using this division of ytn plus 1 over ytn, and that gives us this tn plus 1 minus tn is nothing but a step size h. Okay, so that is what I'm using here and writing finally e power as lambda h. So in numerical method, now we can obtain any numerical method, we can obtain. Let me make it little small. Okay. So in numerical method, we can obtain now by approximating exponential lambda h. Okay. So and this can be done in a various way. So such as we can uh, do it as 1 plus lambda h, means you write the you have to truncate this series up to the first order only. So this gives us the first order method, which is already we have studied, and it is known as the Euler method. And if we can also approximate it by second order approximations, like using the trapezoidal method. So for this we uh, we have this approximation as 1 plus lambda h by 2 over 1 minus lambda h by 2. There can be many other approximations also. I'm giving you just two examples of first order and second order approximation of the exponential term over here. And first order approximation here actually gives the Euler method, and second order approximation which I am showing here is giving us the trapezoidal method. Okay, since these methods we have discussed, so it will be easy to understand. So suppose we denote the approximations now e to power the capital E lambda h. So this is just the notational part. So I am representing e to the power lambda h approximation as capital E of lambda h. So with this notation, I can rewrite the numerical method in a way yn plus 1 equals to capital E into yn. Okay, so from here, after doing the approximation, we get this numerical method as written in the equation number 2. And from there, now if we add the truncation error, we can write down the exact value of the solution at n plus 1 step. Okay, so Tn suppose is the truncation error involved in the nth step. So y at Tn plus 1 will be nothing but y sub n plus 1 plus Tn, and that is not y sub n plus 1, it is actually, so this will be E lambda h y at Tn plus Tn. Okay, so this truncation error, because we are talking about the exact solution, so this will be this one. From here we are writing. Okay, so E lambda h y at Tn, but then some error is involved, so this truncation error we are adding over here. But on the other hand, we know that what is the exact solution. It is e power lambda h y Tn. Okay, so with the help of this, now we can write down the total error involved at step n plus 1. So that will be the difference between the exact value and the approximate value. Okay, and which gives us this expression minus y Tn plus 1 over y sub n plus 1. So using equation number 2, we can write this difference as written over here. Okay, further this yn, okay, I can I can rewrite as epsilon n plus ytn, because the way epsilon n plus n is written means at n plus 1th step error is written, at nth step also we can write it. Okay, so with the help of this expression, the y sub n is written over here, and then just manipulating the terms over here or just rearranging them, finally we end up with at this step. Okay, so this is at this step we see that it is the sum of the two terms. So first term is giving us the truncation error involved at the point Tn. Okay, but the second term is nothing but the propagation error. Okay, so this is the truncation error first term, and the second term is giving us the propagation error, okay, due to the previous step. Fine, so this is giving us the this is the interpretation of these two terms, and here this E, capital E at lambda h is known as the propagation factor. Okay, so similarly for the next step we can go, means at n plus 2n step we can calculate the error. Okay, so for with the help of this formula which we just obtained, we are writing it. Okay, it is coming in terms of y at t n plus 1 and phi n plus 1. So basically we are just replacing n by n plus 1 in this last step of the previous calculation. Okay, and then rearranging the term, and finally end up again at the expression where the right hand side is having the sum of the two terms. Like the before is previous step, here also the first step will give us the truncation error involved at this step, and the second term gives us the propagation error. Okay, so this is the propagated error. So likewise we can keep on doing, and at n plus 1 kth step the second term will be of this form. Okay, just to follow the steps. The first step it is E lambda h epsilon n, second step E square lambda h. So likewise at the kth n plus kth step it is going to be ek lambda h epsilon n. Okay, so if propagation errors, so this is the propagation error. So truncation error is over here. That's fine. That will always be there. It can be controlled also. So basically now this the the thing is, uh, our error will be, if our propagation error involved into the method decays or at least bounded, then only we will get the good results. Okay. So and when it will be happen, if the condition 4 satisfies, is e lambda h modulus must be less than 1. Okay. So if this condition holds, then we can say that the method is absolutely stable. Okay. So with the help of this test problem, we end up with this condition, which gives us the H, which gives us the condition under which the method will be absolutely stable. Okay. Moreover, what we know, that if this e lambda h is less than e to the power lambda h, then method is said to be relatively stable. Okay. So because lambda is involved and it can be any real number, so there are two cases arises. First one is lambda is positive, second is lambda negative. So if lambda is positive, then this approximation of e power lambda h, the approximation capital E for the exponential lambda h, which we have considered, which these two we considered, right? So whatever this approximation we have considered, we observe that this will always remain less than e to the power lambda h, and therefore these methods will be relatively stable in the case lambda is positive. Okay, so it is uh, true here. But if lambda is negative, then method will be absolutely stable if this approximation, or you can say that this propagating term, not we call it, this is okay, when this e lambda h is going to be, mod of this is going to be less than 1. So in this case, whatever interval, by substituting this, whatever interval for lambda h we will obtain, for that interval we can say that the method is going to be absolutely stable, and this interval is known as the interval of absolute stability. Okay. So through example we can understand it. For example, suppose we take the first order approximation as I have taken in the uh, previously I have shown the Euler method case. So in Euler method case, this E lambda h modulus will be equal to mod of 1 plus lambda h, right? Because your E power lambda h is approximated by 1 plus lambda h, right? So if it is the case, then modulus E lambda h will be same as mod of 1 plus lambda h, and that should be less than 1. And if we just simplify it, we end up with the interval of lambda h as the open interval minus 2 comma 0. Means in this interval we will get the or we will be having the method as absolutely stable. Okay, so whenever lambda h is lying in this interval of absolute stability, method is will be absolutely stable. For second order approximation, which we considered earlier, this condition will end up with the fact that the this method is going to be absolutely stable for lambda h belonging to minus infinity comma 0. Why? Because we are having this condition over here, and this inequality will hold for all negative lambdas, okay, in general. So therefore lambda h will belong to the open interval minus infinity 0, okay, with the negative real line. So such methods are also known as unconditionally stable, because there is no condition for lambda h when lambda is negative. Okay, so this is unconditionally stable method. Fine. So see, following this, we can discuss the stability of Euler method. In fact, for real part, I have already done. So if lambda is real, it is done. So same way for complex value of lambda, also we can discuss it. So if lambda is complex with its real part as negative, what condition we have for absolutely this stability? Condition for the method is the following. Mod of 1 plus lambda h, we can write as mod of 1 plus x plus iy in case lambda is complex. Okay, so we are taking lambda h in the form x plus iy. So if this we do, then this modulus can be calculated like this. and it should be less than 1. With this, we end up with this condition, which shows that uh, it is nothing but the inside a circle. Okay, this is inside a circle which is centered at minus 1 0, and it is having radius 1. So in this region, the method will be absolutely stable. Okay, so it is a region of absolute stability of the numerical method. Similar way, if you discuss the stability of backward Euler method, which is given as yn plus 1 equal to yn plus h, f at tn plus 1, yn plus 1. For this test problem, what we see is here yn plus 1 comes out as 1 over 1 minus lambda h yn. So here your term, which is approximating exponential lambda h, okay, is nothing but 1 over 1 minus lambda h. So for real values of lambda, what we get is mod of E lambda h, meaning 1 over 1 modulus of 1 minus lambda h is less than 1. And that will hold for all negative lambdas, right? So it means here also the method is absolutely stable for all lambda h belonging to the negative real line, okay? But in the case when lambda is complex with the real part of lambda is less than 0, by taking lambda h as x plus iy, what we see is this region we obtain as the region of absolute stability for the numerical method, which is backward Euler method. Okay, so this is nothing but the circle. This is the region outside the circle centered at 1 0 and radius 1. Okay, fine. Oh, sorry, this is in this case what I am doing is x is equal to 1. Yeah, this is x part and this is y part. So imaginary part, and this is this part. Okay. So here what we further what you should note that here real part of lambda is negative. So basically x is negative. So outside this is the region of stability. So but at the same time x is less than 0. So this is not the part of stability. Only this plane, this half plane, negative half plane will be the stability region in this case. So that is to be noted in this case. So this is the way we can discuss about the stability of the numerical methods. So just two example I could discuss here for the stability, the Euler method and backward Euler method. But following the same things, you can also think about the stability of the trapezoidal methods and any other methods. Even for multi-step methods also we can discuss about stability. So with this I would like to stop. So if any questions you may please ask.
Thank you, madam, for a very wonderful lecture. Participants, do you have any question? So, if there's no question, let us again thank to the speaker, Professor Shruti Dubey, madam. And the lecture recording would be available on the Canvas platform through YouTube channel. The participant, those who have missed some part of the lecture, they can again go through the lecture by seeing the YouTube recording. And now Professor Ashish Avasthi ji has already joined. Another lecture is by Professor Ashish Avasthi ji. So I welcome you, sir, again to this FDP. I request you to please share your slide and please start your lecture. Over to you, sir.
Let me first stop sharing. Yeah.
Am I audible now?
Yes, sir, you are audible.
Good morning.